Welcome to this primer on the well-ordering principle. In this lecture, we'll look at an illustration of the functional form of the well-ordering principle, or what I call the functional form anyway, because I do not think there is any standard terminology of that sort. So what does it say? It says that suppose we have a function from a set S to the set of natural numbers. Then there is some element in the set S such that the value of the function at that point is at most the value of the function at any other point. Okay? So it's a very simple statement. It just follows from the usual well-ordering principle. And at the same time, here we cannot ask for uniqueness of this point, clearly. Alright, so we saw all that earlier, and now we will see how to apply such a thing. So what we will be doing is showing the classical result that this number is irrational. In other words, it just means that there is no rational number whose square is 2. Okay. So what we are asking is to show that this equation is not solvable in integers, meaning you cannot find integers x and y such that this equation is satisfied. But since this is positive, it is same as asking for natural numbers x and y for which this equation is satisfied. So a reformulation of the problem would be to consider the following set. It's all pairs of natural numbers such that this equation is satisfied. So the problem is only asking us to show that S is empty. This means want to show that. So this is what we want to do, and by way of contradiction, we will assume that S is non-empty. Okay, now that S is non-empty, we can define a function as follows. Right, that is our definition. And one should think of f as something that is measuring the size of any given thing in the set S. More precise notation. Okay, so think of f as something that measures the size of the input. This is just one notion of size. Other notions of sizes will also work. This is the most convenient for this argument as far as I'm concerned. Okay, so let's see. So now by the well-ordering principle, or the functional form of it, there exists an element a comma b in S such that this is smallest possible. Again, when I write f a comma b, when I write this, I really should be writing this, but I hope you do not get confused. For all pairs in the set S. Okay, fine. Now, for the moment, we should turn to a picture. So think of maybe give me a second. Yeah. So what we are given is since this is after all an element of S, we have a by b equals root 2, which is same as saying that a square is equal to 2b square. So just focus on this equation, a square is equal to 2b square. Geometrically, we can interpret this as draw the square with side a. So this side length is a, and draw the square with side b. And now what this says is that 2 copies of this square have the same area in total as the area of this square. Okay, so what we can do is we can try to cover this with 2 copies. Of course, there will be overlap. Okay, so what we have been provided by this equation is that this area plus that area is the total area of the big square. Okay, and if you think about it, I'm going to shade a few things. So there is this orange area. This orange area must be equal to the total gray area. Okay, so pardon my shading, something has fallen out, that's okay. So if you just think about it, this means that the orange area should be the same as the total gray area. And once you agree with that, let us figure out the expression for the orange area and the gray area. So if you find, both of these are squares, these are just squares, and this is also a square. So let's just find the side length. What is this side length? This is A minus B. Maybe I'll write it here. This is A minus B. I think that is correct, because what is this length? This is total length minus that length. Total is A and that much is B, because this is the square with side length B. So this little square has side length A minus B. Same for that. You can think about it. For the orange part, what is the side length? Well, this much is B and this is A minus B. So this is B minus A minus B. So therefore the side length of the orange square is 2B minus A. Okay. So therefore from this picture we see that we deduce that A minus B whole square and twice, because that is the total gray area, is equal to the orange area, and the orange area is 2B minus A whole square. Okay. Right, that is from this geometric argument. But if you do not like the geometric argument, you can just open these things out and you will see that this equation holds. So this is just, an algebra. You can arrive at this by an algebraic inspiration. From this equation, if you just manipulate it around, you can get this equation. But it is good to see a geometric motivation for it. Okay, so we have that. And now here is something that we should notice. Note that first of all, A is greater than B. Why is that? Because just look at this equation. Since A square is 2B square, or you can look at this equation, it's even easier. So since A is equal to root 2B, this is greater than B. So A is greater than B. And similarly, you can show that 2B is greater than A. Again, you can look at this equation again. So this says A is equal to root 2B, which gives us that root 2A is equal to 2B, and hence 2B is greater than A. So we have both these things, and hence these numbers are both natural. So 2B minus A is a natural number, and A minus B is also a natural number. So basically this pair is in n cross n, which satisfies, because of this equation, it is not just in n cross n, it is actually in S. This guy is actually in S because this equation is satisfied. So I will write an S here. Okay. Fine. But at the same time, f of this pair A minus B and 2B minus A, what is this? This is, by definition, which is equal to B, which is less than A plus B, and this is equal to f of A comma B. But that means f of this particular thing A comma B. Note that this was legitimate only because this was a member of S, right? So it is important to first establish that this is an S, and only then we can write this. So we have that. But this is a contradiction to the fact that this, the F value at this element is the smallest possible amongst all F values. However, this is telling us that no, that is not the case, because this particular F value is dominated strictly by that. So this is a contradiction, and we are done. Okay, so that's an illustration of the functional form. At the same time, nobody is going to write these proofs in this detail. How we do it is we just write one line. We say, let us start with a pair A comma B of natural numbers with the smallest possible value of A plus B, such that A by B is root 2. That one line is covering this much. And the rest of the proof will go through as it is. Okay, so I hope you were able to follow this proof. It is important to follow this proof. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.